Alright, today I will be going over my recent work on the regression analysis of scan parameters for histotripsy treatment of Staph aureus biofilms on surgical mesh. And before I begin, I'd like to acknowledge my collaborators on this work, Clayton Thomas and Dr. Wu, and I also would like to acknowledge my support that was received to do this work from my recent NIH R21 grant. I have nothing to disclose on this financially. During this talk, I'll go over the objectives of my study. I will also discuss the methods utilized to obtain my results. I will then summarize the results that were obtained and give conclusions based on those results. So our objective is to develop a new way to treat infections on medical implants. Eventually we would like to take this to any implant, but for now we're focusing on surgical mesh. And surgical mesh has become relatively standard practice in hernia repair, with mesh infection rates of about 1 to 10%, requiring removal about 70% of the time. And this is not unusual. Most implants, when they get infected, need to be removed, which is why we're hoping to develop non-invasive treatments for infections, in particular mesh infections at this point. Now, the goal of this study was to determine the relationship between the scan parameters and the level of biofilm destruction on the mesh to guide future experiments. Specifically, we would like to maintain efficacy, as we observed in our earlier studies, while at the same time reducing the time it takes to do the treatment. So for our work, we grew the bacteria on mesh samples by putting Staph aureus biofilms on a 10 millimeter by 10 millimeter samples of polypropylene mesh over 6 days. The meshes were placed individually in 20 milliliters of TSB and transferred to a new container with fresh broth each day after being inoculated, of course, with Staph aureus on the first day. Then prior to exposure, we rinsed with PBS and inserted into Aquaflex ultrasound gel pad standoff vessels. Now, these gel pads are sterile and reproducible, and so they provide a nice repeatable target that we can use to insert the mesh into. They also have the same mechanical properties as the abdominal wall, and so when you're working with histotripsy and cavitation type treatments, the mechanical properties is the most critical, and so that's what we wanted to duplicate. Now, when we did our exposures, we focused our transducer on the mesh, and then we continuously scanned the transducer in one direction, took a step, and went back in the other direction, and did this until we reached the end. And this would be our raster pattern, kind of continuous step until we reached the end. Once we reached the end, we went back to our initial location and repeated the process to expose or pass over the mesh additional times. And we went from 2 to 6 passes over the mesh. And we wanted to see whether that had an impact on efficacy and treatment time. Now, we also varied the step size. That's the step between these scans, and we also varied the speed of the scan. And so here was those parameters. The step size was varied from 0.25 to 0.5 beam widths. The scan speed was varied initially from 0.3 to 1.4 beam widths per second, although later on we restricted to a narrower range based on the results before we did the regression analysis. And the focus was passed over the mesh 2 to 6 times for each exposure. Now, the transducer itself was a 1.3 megahertz transducer with a 6.3 centimeter focal length and 8.2 centimeter diameter with a 4 centimeter hole, which we could use to put a imaging transducer in the future. The PRF, or pulse repetition frequency, was 500 hertz, with each pulse consisting of approximately 3 cycle tone bursts, and the 3 dB beam width of our device was about 0.7 millimeters as measured by a wire target. And so here's our experimental setup. We had the function generator and high power amplifier going into a matching network that was then feeding our transducer, and the transducer, which was mechanically moved during the exposure. The mesh was in the center of the gel pad sample. All of this was inside of a water tank. Now, of course, calibration is critical in order to get reproducible results, although when working with these high pressure waveforms, you can't just put the hydrophone at the focus and hope you get good results. First of all, you get cavitation. All of our exposures show cavitation when focused on the mesh, and so instead you need to use modeling. Now, the hydrophone would be damaged due to the cavitation if you tried to use the hydrophone, and in addition, of course, there's effects that you have to take into consideration: the size of the hydrophone element and the frequency response of the hydrophone, which makes making measurements at high pressure fields very challenging. And so the better approach is to model it after you've made some measurements. So we measured the ultrasound waveform in the prefocal region using a hydrophone, and then extrapolated into the focal region using K-Wave, which is a free software that's available for that. Shown here is our peak compressional pressures and peak fractional pressures in the focal region. Obviously, they look differently in terms of their shape because of nonlinear propagation, and that's even more emphasized when you look over here in terms of the time domain waveform. So here we have the time axis and the pressure, and these two curves correspond to the location of max peak compressional pressure in blue and max fractional pressure in red. And you can see they're highly distorted, highly nonlinear, a lot of harmonic content here, which is what happens when you go to these high intensities that are used in histotripsy type of exposures. Now, one of the things we had to be careful of is our exposures, if we vary over these ranges here, are going to vary quite drastically in terms of how long the exposure take. And remember, the mesh is sitting in here inside this ultrasound gel pad without any nutrients. So we wanted to make sure we weren't accidentally introducing an artifact based on exposure time or time in the tank. And so here we have the surviving colony forming units on the mesh as a function of time, spanning the entire range of times that we considered in our experiments. And we can see that there's no impact on time. And so we aren't introducing an artifact by having such large treatment times in our experiment. Now here is the results from each of the mesh. Now when we were doing our analysis, we did not try to sample every single possible value of these parameters. That would have taken too long and defeats the whole purpose of doing the regression analysis to narrow down the parameter space, if you will, which is what we were hoping to do with the regression analysis. And so instead we had a subset, and here is a subset of those exposures that we considered. And so the top line is the speed. Obviously we have 1.4, 0.7, and 0.3 beam widths per second. The next line is the step size that was utilized, and the last line is the number of passes which we did over the mesh. And these were selected based on our earlier results, where we were expecting that the more passes at a faster speed would be better, but it actually turned out that that was not the case, as we'll see when we get more into our results here. And this, of course, is our sham case, and so you can see what the reduction is for each of these experiments. Now, after completing the experiments and before doing the regression analysis, we did an ANOVA to see what was significant, and we found that they were all statistically significant with the exception of the 0.7 beam width per second and 1.4 beam width per second scan speed. Those were not different. There seems to be some sort of plateauing effect that's occurring here that's not going to be captured by a regression analysis. And so rather than digging deeper into that, we focused instead on the faster scan speeds, which, as we can see here, gave us our better reduction in numbers of colony forming units. And so we did our regression analysis only considering the 0.7 and 0.3 beam width per second cases. And the red line here shows that final regression analysis for these cases. And obviously it does not agree with the 1.4, but that's to be expected because that's outside of the range of the analysis. And in general, regression analysis is only valid in the range of the parameters tested. Now, in the range tested, it does have reasonably good agreement. So here is the number of colony forming units remaining on the mesh as a function of these different parameters. So S here is scan speed, delta is step size, and P is the number of passes over the mesh. And so here is a graphical representation of the same equation, and we can see that we have a very strong reduction in the number of colony forming units on the mesh as we reduce the scan speed. And of course you see that because of that 4.8 dependence on scan speed. The number of passes has a relatively small impact, and these two curves surfaces here correspond to two different passes, and so there's a very small impact on passes. Now there is an impact on step size, but there's a relatively small range over which you can really reasonably vary the step size. And so really the scan speed is the most critical. Now once we did the regression analysis, we could also use that to predict which parameters would give us the best performance in terms of maintaining efficacy while also reducing the time. And so this is a normalized time for the parameters where we still wanted a 5 log based in reduction in the colony forming units. And so here we have the number of passes, and here we have the scan speed, and on the vertical axis we have the normalized time. And the blue corresponds to 0.25 beam widths per step, the red is 0.375, and the green is 0.5. And you can see then, to get to these really small times, we want to perhaps reduce the beam width just a little bit, but the main reduction is scan speed. We want to go to a smaller scan speed, and we want to reduce the number of passes. Now, in addition to the blue, red, and green corresponding to our regression analysis, we also have this star here, which is the results from the present study, which lands right in where we would expect it to be. and the diamond are results from a previous study also showing good agreement with our prior results. And so in the future, we're going to want to move to a system that has fewer passes. Basically, one pass should be best. And we also want to move to the case where we have a very small or slow scan speed. That will give us the best in terms of time and treatment efficacy. So, high-intensity therapeutic ultrasound can successfully destroy Staph aureus biofilms. Reducing the number of passes and scan speeds should allow for more efficient biofilm destruction in the future, reducing the treatment times, and that's the direction in which we're headed now with our research. Feel free to contact me if you have any questions. I appreciate you taking the time to listen and watch this presentation, and thank you for your interest.